The next talk is the Best Paper Award-winning paper in track B. The speaker is Henry Sinclair-Banks, and the authors are Marvin Kuhneman, Philip Mazowiecki, Leah Schutze, and Karol Veritsky. Sorry, many apologies for mangling these names. I tried to learn them before, but I still messed them up. The paper is on coverability in vector addition systems with state, revisited, improving Rackoff's bound to obtain conditional optimality.
Thank you. Good afternoon. My name's Henry. I'm a PhD from the University of Warwick. And today, indeed, I'm going to be talking about the coverability problem in vector addition systems with states. I understand that this might be a near impossible read for many of the audience. Don't worry. I'll be giving a nice intuitive introduction to the problem. I'll then work through a little bit of the context on the history and the complexity of the problem to then be able to give you our contributions. I should make mention and thank my wonderful co-authors, Marvin Kuhneman, Philip Mazowiecki, Leah Schutze, and Karol Veritsky. Okay, let's begin. So I'm going to give you a problem on directed graphs with weights like this one here. So I'm going to ask from a node A, can you reach a node G on a path that's never negative? When I say never negative, what I mean is as you step along the graph, you sum the weights of the edges that you see, and I want to make sure that that sum remains non-negative at all times. Okay, so in this exact instance, you'll be starting at A and you'll have sum 0. You'll then notice that you can't go to C because you would take -7. This would lead you negative. So you add 2 and you go down to B. From B, you can go up to C. You'll have sum 5, over to E with sum 3, down to D with sum 7. And now, indeed, you can just jump over to G and you get there with a never negative path. This is a pretty easy problem. If I gave you a few minutes and maybe a coffee, you'd be able to come up with an efficient algorithm to solve this problem. So let's make things more interesting. Let's have 2 components on every edge. So we'll ask the same kind of question. From A, can I reach G on a path that's never negative on any component? So we'll start with sums 0 on both components, and we'll add all the first components to the first sum and all the second components to the second sum. So indeed, we'll start at A with 0, 0. We'll then move over to B, and now we'll have sum 2 on the first component, and we'll keep 0 on the second component. Now we'll step up to C, and we'll have sum 5 on the first component and sum 8 on the second. E with 310, D with 75. But now look, you can't step to G directly, even via F, because you'll get killed on the second component. So you have to do something a bit more intelligent. You have to think for a while. Maybe you need 2 coffees this time. But notice there's a cycle. If you go from D to A to B back to D, you'll get 1 on the first component and 10 on the second component. In fact, you can take the cycle as many times as you like. And you'll get your counter values, or your sums, sorry, as high as you like. And from that point, you kind of are no longer scared of negative edge weights. It turns out that doing this twice is all you need, and then you can step directly over to G. And indeed, this is a never negative path. So this is a positive instance. It's much more difficult, right? Like thinking of an efficient algorithm for this problem requires a lot more thought. But I'm not done. I'm going to make it more difficult. I'm going to add more components. In fact, I can add as many components as I like. I've spared you from 3 components or 4 components or 5 components, but I've really tricked you. You've been looking at vector addition systems with states without realizing, and you've actually been thinking about the coverability problem. So the coverability problem asks from some node P, can you reach another node Q via a path that's never negative on any component? The acronym VASS is what vector addition systems with states stands for. I'll kind of bring you into my language. I don't call these things nodes, I call them states. I don't call these things edges, I call them transitions. And I might call the sums counters as I go along. Okay, briefly, a little bit of motivation. I'll give you 4 reasons quickly why one might study this problem. The first is you can imagine some sort of maybe perhaps silly resource management problem where perhaps you have a hybrid car with some petrol fuel tank and some battery, and you can imagine associating a cost, like a fuel cost and a battery cost, to every road that you perhaps try and traverse around Paderborn. And you can ask a question like coverability, which is, from my home, can I reach my work via a path that's never negative? You don't want to run out of fuel and you don't want to run out of battery. You could also see VASS as an equivalent model to Petri nets, which is a famous model of concurrency, which has just about decidable reachability. You can also think about coverability as like safety analysis. So imagine you model a system as a set of control states and a set of actions. You can now ask a coverability-like problem that goes, is there a sequence of actions that takes me to some state? If you define a set of bad states, then coverability is really like asking, oh, can I reach a bad state? This is an unsafe system if that's true. And finally, there are some lovely related problems. First is unboundedness, which asks, from some initial configuration, can I reach an unbounded number of configurations? There's reachability, which is fussier than coverability in a sense. Rather than just reaching a state, I'd like to reach a state, and perhaps my sum must be exactly equal to 0. And then perhaps more historically relevant, it turns out that this problem is equivalent to some specific word problems on commutative semigroups. Okay, so right, now a bit of history and a bit of complexity. But before I give this, I must define the size of the instance of the problem. So I'm going to reserve 2 letters, D for the dimension, that's the number of components. In the very first, you had D as 1, in the second, you had D as 2. And I'm going to reserve n for the size. I'm going to encode these in unary, so you just sum up all the numbers you see on your graph and maybe add the number of states. Okay, so first, in 1976, already this problem was known to require exponential space, thanks to Lipton. And 2 years later, Rackoff then showed that this problem is decidable in exponential space. So it doesn't take a genius to stare at this and go, well, this problem's exponential space complete. And I don't hear a question from the audience, but why am I talking is a fair question to ask. Let's take a closer look. So what Lipton really said was that coverability in VASS requires 2 to the d times log of the size of the VASS space. The way he went about this was by finding some kind of nasty instances that require really long runs, doubly exponential length runs. They are appropriately called Lipton's construction. To give a little bit of a flavor as to how this would even come about, let's just look at one little example. So I've got 5 components here, and I'll just say that if there is an edge that's unlabeled, that's just all zeros. So to get to Q, you would need at least 1 on the final component. To get 1 on the final component, I would need to take that final cycle at least once, right? And to get at least 1 on that final component, I would need at least 2 on the penultimate component. And to get at least 2 on the penultimate component, I need to fire the previous cycle twice. And to fire the previous cycle twice, I would need at least 4 on that middle component. And to have 4 on the middle component, I'd need to fire that middle cycle 4 times. This continues, right? And it doesn't take much to observe that imagine there were more than 5 components, right? Imagine there were d components. This would require exponential in the number of components length run to witness coverability. That's a far cry away from what Lipton did. That's a double exponential. I don't have the time to explain Lipton's constructions as much as I want to, but that's just to give a bit of a flavor. Okay, so what Rackoff did was complementary. He argues that coverability in VASS can be decided in exponential space. That's 2 to the d log d times log of the VASS, log of the size of the VASS space. And his idea was to argue inductively that there are, I'm going to say short runs. It's kind of perhaps not fair to call them short, but the runs are bounded by, at most, n to the 2 to the d log d, this double exponential value. And already this was asked as an open problem in a neighboring context by Mayer and Mayer in 1982. They just asked to improve these bounds. In reality, they asked perhaps partially for bidirected vector addition systems with states, but they did also ask for the non-bidirected case, which they actually phrased in commutative or non-commutative semigroup problems. And then just a few years later, Rosier and Yen made a fantastic piece of work that I think this slide wouldn't be complete without mentioning. They kind of stated all of these results in much more modern terms. So really, these theorem statements that I've written down are thanks to, well, Rackoff, Lipton, and indeed Rosier and Yen. They sort of split the size of the VASS into the number of components, the number of bits required to write down the transitions, and the number of states. Okay, so our contributions. We, as the title and what it's probably not a surprise anymore, is it, right? Coverability in VASS is always witnessed by doubly exponential length runs. The improvement being over Rackoff's that we shaved this double exponentiated log d factor, this gives 2 corollaries. The first is that coverability in VASS can be decided in exponential space. That's 2 to the d times log of the size of the VASS space. Alternatively, by using some sort of fairly trivial exhaustive search algorithm, you can also get a time algorithm that's doubly exponential. This isn't special to our idea. You could have taken the same algorithm out of Rackoff's bounds, but you would have more expensive time. It would be like n to the 2 to the d log d. I also highlighted this as optimal because it matches Lipton's lower bound. And the conditional optimality in the title references this fact, which is that assuming the exponential time hypothesis, coverability in VASS requires doubly exponential time, which matches the algorithm that we get from our upper bound. And this is therefore conditionally optimal. I'll talk about ETH shortly. There are also 2 more contributions that I will not be talking about in this presentation, but if they pique your interest, please come and query me, quiz me, and find out more afterwards. The first is that under the K-cycle hypothesis, with just 2 dimensions, right, d is 2, coverability requires what we expect to be quadratic time, and the other statement is that under the K-hyperclique hypothesis, coverability in so-called linearly bounded VASS requires some amount of time. Linearly bounded VASS are just VASS where the maximum values that the sums take is a multiplicative factor of the constant multiplicative factor of the size of the VASS. And this is very close to the upper bound that's known for this problem, so yeah, never mind. We'll be talking about the top 2 statements. So how do we improve Rackoffs? So, as we just had, coverability in VASS is witnessed by double exponential length runs. The idea is to use Rackoffs bounding technique, but we use much sharper, more finely chosen counter value bounds. So to just give a little bit of a flavor for Rackoffs, just very high level, Rackoff chooses a certain value to bound the counters and says that, well, if I ever see some set of counter values that exceeds this bound, so you leave this large green cube or hypercube, then in a sense you can forget about this counter. It's so large, it's so much bigger than what the target will be that you can effectively forget about it. All negative updates it receives later are not to be concerned by. And then you can do induction by, in a sense, removing that component from your VASS and repeating. We do the same thing, but we choose a different bound. So rather than bounding all counter values by the same value, we bound them by different values. So we notice that the largest value, or the largest counter, needs to be bounded by the same value that Rackoff chooses, but the second largest doesn't need to be so great, and the third largest doesn't need to be so great. And we do the same thing. If you ever see a configuration that lies outside this box, then, or this sort of box, then you can induct, you can forget that counter value and move forwards. To give an intuition about this shape in higher dimensions, imagine a shoebox. A shoebox is like so wide, it's wider than it is deep, and it's deeper than it is tall. It's like a sort of cube, or not cube, it's like a rectangle of side length 3, 2, and 1, right? And in this case, in dimension 2, it's something of side length 2 and 1, and you need all permutations of how this thing fits into the origin. But in 3 dimensions, you can imagine trying to jam your shoebox into a corner of a room. There are like 6 ways of doing it, kind of like this, right? And our shape is the union of this thing. And I gave this analogy to someone, and they really liked the analogy. And their response was like, oh, I can 3D print this really easily. So rather than spending a lot of time on ticks trying to draw this, they just made it for me. I came to my office the next day, and they 3D printed this thing. And so thank you, Alex. It's fantastic. And it actually gives you some like visual representation of how much smaller this thing is than the cube that bounds it. I don't know what a hyper shoebox looks like, so I can't generalize my comments further. But there you go. Okay, a little bit more detail on how we go about this. So we have shoeboxes of side lengths M1, M2, M3, etc. I'm just going to give the 2-dimensional case here. Imagine you're looking to find a path for coverability where you're starting at some values U and you're looking to cover some values V. I've kind of very cheekily forgotten about the states. I'm just focusing on the counter values. Those in the know with VASS know that this is fine. If you are not so familiar, don't worry. It's fine just to ignore the states. And so we're interested in this instance from U to at least V. Imagine I give you the shortest coverability run from U to some values W. Note that W will be at least V, right? So it's going to be above and to the right of V. I'm going to call this shortest run pi. And then I'm going to split pi about the first configuration that we call non-thin, where thin just means I lie inside this shape. I'll call this thing x. I'll have a thin part of my run in blue, and I'll have the tail of the run in orange. So the thin part of the run can't be that long. It could, in theory, see every single thin configuration. Note that if you ever repeatedly see like the same configuration twice, then you found a cycle that has overall zero effect. You could remove that cycle from your run would be unchanged, but it would be shorter, and that would contradict the fact that you've chosen the shortest run. So in theory, this blue run could really wiggle around all of the shoeboxes, but at least we know it's bounded above by the number of configurations in the shoeboxes, so we can say that the length of this blue part is bounded above by, well, the size of a hyper shoebox is, what, M1 by M2 by M3, etc. And there are de factorial many ways of shoving it into the origin. And then the tail of the run, well, look at X, right? X has its first component way out to the right. Notice it's way beyond M1, way out there. In a sense, we can forget this. I'm not going to go into too many details now, and we can do induction on just the second component, and we can argue that, well, the tail of the run is bounded above by this MD value. I won't go into details. Unfortunately, I don't have enough time. And so together, when you combine these two things, you, with carefully chosen M1, M2 that are roughly doubly exponential in N and in D, that you get the bound that we're interested in. OK, so if you remember a little while ago, I said that there's an alternative algorithm that exhaustively searches the space of configurations using some sort of trivial algorithm that runs in doubly exponential time. How do we get a conditional matching lower bound? So we say that assuming the exponential time hypothesis, that coverability in VASS really requires this doubly exponential time. So the exponential time hypothesis very roughly says that an n variable instance of SAT requires 2 to the n time. The corollary that we care about is that there are no n to the little OK time algorithms for finding a k-clique in a graph, and our reduction is therefore to look for an exponential sized clique in a graph by solving some coverability instance in VASS. I would love to show you the reduction, but there's many steps involved. We use old techniques from Rosier and Yen. I don't have enough time to do that now. But if you just shove k equals 2 to the d in the statement from exponential time hypothesis, you'll see you get an n to the little o of 2 to the d, which very closely matches the theorem statement that I've provided for you. And so then we can conclude that our time algorithm is conditionally optimal. OK, so to conclude, I'll just restate that we have a new bound that improves on Rackoff's in that the length of coverability runs is bounded above by n to the 2 to the d, shaving off that log d factor. That allows us to draw upon two corollaries, either exponential space or doubly exponential time algorithms for coverability. The space algorithm is unconditionally optimal from Lipton, and the time algorithm is conditionally optimal from our ETH reduction. I leave you with one open problem, which is right back from the start of the talk. So if I ask for a VASS with just one component, can coverability be decided in sub-quadratic time? So it doesn't take too much to find out that it can be decided in quadratic time. This would sort of conditionally separate it from coverability in 2VASS, which we use the case cycle hypothesis to argue requires quadratic time. But it's kind of related to a problem of finding either the shortest path in a graph or finding a negative cycle. It's actually kind of the inverse of this problem, for which I think only last year a slightly superlinear time algorithm has been found. I think this problem is being worked on. You can imagine it as just modeling an electric vehicle's battery, and from every place you jump around by spending battery or gaining battery, maybe by regenerative braking or something like this. And you're asking, really, can I get from some location to another? So it's an interesting problem, and I think this is a very hard problem, unfortunately. OK, I will finish there. Thank you very much.
Questions? Let me start by asking a question myself. So can you say a little bit more about these hypotheses, the K-cycle hypothesis? And forgive my ignorance, but I haven't heard of these.
Yeah, so the K-cycle hypothesis asks, given a graph, well, OK, the K-cycle hypothesis states, given a graph, you require quadratic time to find a cycle of length k in such a graph. And then the K-hyperclique hypothesis is the same kind of thing. If I give you a hypergraph, a three-uniform hypergraph to be precise, detecting whether there is a K-hyperclique in that hypergraph requires n to the k time.
OK. And do you have some quick intuition for why that's tied up with coverability in 2 dimensions, for example, for the K-cycle hypothesis?
Yeah, so we can build a VASS which only has a coverability run if there is a cycle in the original graph.
Okay.
The intuition, I just have to draw you the picture. It's very simple.
Yeah, okay. Any other questions? Oh.
So thank you for the talk, very nice. So can you give some intuition about the lower bound, so how the clique problem
Okay, I'll give a brief. So we associate a unique prime with every node. A clique is then, or a choice for a candidate clique is then a product of k primes. So then if you guess a product of k primes, you can check if it's a clique by doing 2 divisions. So an edge has 2 nodes, right? You can divide by the endpoints primes to your candidate k product of k primes. And if you succeed with every edge, then you know that your candidate indeed is a prime, indeed is a clique, sorry. We do this first with a VASS with 0 tests, which is dangerous, I understand. So we do this divisibility checking using 0 tests. But we don't use very many 0 tests. And actually, the VASS we construct is structurally bounded. And Rosier and Yen have a lovely statement that says, well, if you have a bounded VASS that has access to 0 tests, then with a linear blow-up encounters, you can simulate instead of having 0 tests, just have a regular VASS. So we have this in 2 parts. I hope that makes sense.
Any further questions? If not, let's thank Henry.
Thank you.